The first question that we have right there is a problem that requires that we add the numbers. There's a special way in which we add the numbers. Of course, we just don't write the numbers down as we have a mind. We have to take special care as to the way that we write the numbers down. We'll just begin by writing down the first number. The first number, 1699, and then of course, we have there indicated the place values of the numbers, the digits that we have there. So we have ones, tens, hundreds, thousands. And when we are writing the other numbers down, we are going to ensure that the numbers are written down according to their place values also. Next, write 63. Place the ones digit under the ones digit. So we're going to write 63. We have here 63. This digit is the ones digit, and it will go under the ones digit. And the 6 means 6 tens, that will go under the tens digit. We are just going to write down next 107, and we are going to first place the ones digit under the ones digit. So we are going to always write beginning with the ones digit, then the tens digit, then hundreds, and then thousands. Some of the numbers do not have the hundreds digits, so we may leave that one out. So place the tens digit under the tens digit. The tens digit is a 0. Place the hundreds digit under the hundreds digit. Right. And of course we have 5. 5 is 5 ones. We are going to place that 5 in the ones column. Next, we are going to add the numbers. So when adding numbers, of course, we are going to begin with the smallest place value, which is ones. So we are going to add all the digits in the ones column first. So add the digits in the ones column first. In the ones column, we have 9 plus 3 plus 7 plus 5. That's what we have here, 9, 3, 7, and 5. So we will add those. When we add them, we get 24. So we are going to write the 4 down, and we are going to carry the 2 to the tens column. As a matter of fact, this 24 that we have right there means 4 ones and 2 tens. This 2 is going to be taken to the tens column, and the 4 will be written down. Right. Next, we are going to add the numbers in the tens column. 2, 9, 6, 0. Of course, the 2 that we have just carried is a part of the tens column now. Therefore, we are going to add it along with the other numbers in the tens column. So we have 2 plus 9 plus 6 plus 0, and that is equal to 17. Write down the 7 and carry the 1 to the hundreds column. Now this number that we have here, 17, it looks like 7 ones and 1 10. However, don't forget that we are adding the numbers in the tens column. So this 7 here, this 7 right here means 7 tens. So this one is actually 100. So this one is going to be carried to the hundreds column. Next, add the numbers in the hundreds column. 1 plus 6 plus 1, and that is equal to 8. No number to carry this time, so we just write 8 down. There's only one number in the thousands column, and it is written down also. So after we have added these, we have only one digit in the thousands column, and it is written down. So the answer is 1874, and our choice is A, right there. We have another problem. What is 0.03 multiplied by 0.65? Well, I'm very happy that this problem has come immediately after the one that we have just completed. This is because in the one before, in adding the numbers, we put the digits under each other, and we are going to take a similar approach right here. But this one contains decimal places, and not just adding with decimal places, multiplying with decimal places. So we need to pay special attention to the way that we arrive at our answer, especially where we place the decimal point in our answer. So we are going to multiply the numbers as in regular multiplication, because we are multiplying 0.03 by 0.65. And we are just going to multiply them as regular multiplication. Of course, we could have placed the 0.03 as the multiplicand and the 0.65 as the multiplier, but we have chosen to take somewhat of a different approach because we have a single digit right here, single non-zero digit, which will help our process of multiplication. So we are going to begin with 3 times 5, and that is 15. So of course we are going to write down the 5 and we are going to carry the 1. So 6 plus 1 is equal to 7 will go here. Is that what we do? Okay, no. So we're not going to do that. We are going to multiply 3 by 6 first. So we're going to say 3 multiplied by 6, that is 18, and then we add the 1 to that. So 18 plus 1 is 19. So we are going to write the 1 down and we are going to carry the 3. Be careful in the final step not to say 3 multiplied by 1, but to say 3 multiplied by 0. Remember, the 1 is a carry from the previous column. So 3 times 0 is equal to 0 plus 1, and that is equal to 1. Now, we have 3 non-zero digits, but how do we determine where the decimal point will go? Notice we have not considered to put the point right there as yet. As a matter of fact, that is not a correct approach. Where do we put the point? When multiplying numbers that contain decimal fractions, the rule governing where the point is placed is different from the rule for addition, in which a point is placed vertically below the other points. The answer is required to have the same number of decimal places as the total number of decimal places in the multiplier and the multiplicand together. So let us count the total number of decimal places, and Jerry, you'll have to be very quick, else we'll count the number of decimal places and you don't realize. So let's go. Well, I know you did not see that, so we're going to do that again. We have 1, 2, 3, 4 decimal places. Remember that in a number that does not contain a point, the point is considered to be at the extreme right. So we're going to place the decimal point 4 places to the left. Of course, right here is where the point is considered to be. And we are going to place the decimal point in the end 4 places to the left. Do not forget now that we have 1, 2, 3 places of decimal right here. But our answer requires 4 places of decimal. Therefore, we will have to include a 0 as a placeholder in order that we can complete the total number of decimal places. 2, 3. We put our placeholder in 0, and that is where our point will be. Of course, it's not a complete necessity to have a 0 in front here, but it has some very good reasons for being there. As a matter of fact, it shows that the number that we are considering has no whole number part whatsoever. So that is why this 0 is there. If it is not placed there, we can still come to that conclusion, but placing it right there does make our intention clearer. So our answer is option C, And as you can see, we have 0.0195, and that is option C. Here we have another one. What is 10 minus 0.925? So let us write the 10 down. We will soon subtract a number that contains decimal places. We will include the decimal point at the extreme right. So the number that we are going to be subtracting from the 10 is a number that has decimal places. So it would be good if we would write the 10 as a number that has decimal places also. No decimal place without decimal point, so let us put our decimal point right there. But how many decimal places do we use? The number to be subtracted contains 3 decimal places, so we will use 3 zeros as placeholders. Because this number that we are subtracting has 3 decimal places, we are going to write a number here with 3 decimal places also. So we are going to write 0.925 in such a way that the point is exactly below the point in the 10, of course, 0.000. So let us put that there. Notice that the points are aligned with each other. Now we are going to subtract. We now wish to subtract, but our first task is to subtract 5 from 0. We cannot do this, and therefore seek to rename the first digit that is not equal to 0. As a matter of fact, we seek to rename this digit first. But because it is a 0, we cannot get any value from it. So we have to go to the other one. And we try to rename this also. And we continue on and on until we get to this one that we have right there. So that is the one that we have to rename. When we rename that one, we don't jump all the way over here. We have to take it in sequence, beginning with the digit that is next of kin to the one that we have right here. So we're going to go here first. So we take this out, and do not forget that while the digit is moving to your right, it is going to be always representing 10 times the other one. So although we take a 1 from here, when it gets here, it is 10 times. So we have a 10 there. So we have to continue with the renaming process. 9. And of course, if you are going to go all the way down here, you imagine what will happen. Another one, rename to 9, and then we do the same thing until we get our heart's desire. So now we're going to say 5 from 10, and that will give 5. Then we say 2 from 9, and that is 7. Then 9 minus 9, and that is 0. And of course right here, 0 from 9, or we say 9 minus 0, that is equal to 9. But of course, good that I have this computer to assist me. I was just forgetting that the point needs to go down, and it says here, the point will go below the point. So we need to put the point so that it is aligned with the other 2 points that we have right there. So 9 minus 0 is equal to 9. And of course, there is no other non-zero digit. And our answer is 9.075. And of course, that is going to be option A. That is representing option A. Right there. Which will give the value of the underlying digit in 9,836. Well, the fact that I say 9,836 should tell you that the underlying digit, which is the 9, is 9,000. And of course, no problem seeing that option C is correct. However, let's see if we can make that very clear by giving you a visual representation of the solution of the problem. So let us first write the number down. 9,836. 9,836. So we will next identify the place values of each digit. There, we have identified them: 6 ones, 3 tens, 8 hundreds, 9 thousands. The underlying number has a place value of thousands. The face value of that number is 9. Its actual value is equal to its face value multiplied by its place value, which is 9. So 9 is the face value and its place value is 1,000. So 9 multiplied by 1,000. And of course, the answer is therefore option C. What is 12.15 divided by 3? What do we do first? First, we're going to say 3 into 1, and we can't. We could put a 0 right here, and we would encounter no harm in doing that. But it's not in line with what we are accustomed to doing generally in mathematics. So we don't have to put that 0 immediately. So let us first attempt to divide 3 into 1. Of course, we cannot do that. So we are going to eventually say what? 3 into 12. So 3 into 12 goes 4 times. Good. And of course, let us not forget our point. The point will then be placed vertically above the point that is there. So we're going to put our point vertically, which is right there, just above that point. Then we're going to say again 3 into 1. We have to take our division digit by digit. So 3 into 1. We can't. So this time we'll have to put a 0, because that 0 has a value right there. Not a value in terms of its face value, but it has a place value right there. So it is important that we include that 0. And of course, our next step is to say 3 into 15, and that will go 5 times. So our answer is therefore 4.05, and that is represented by option D. What digit in 2,479 has the greatest value? The value of a digit in a number is dependent on two things. One is its place value. And of course, we have the place values right there. In this section, we have already seen place values of numbers, and this is just another case. The place value is dependent on the position relative to other digits. So the digit farthest to the left will have the greatest place value. The place value is the greatest determining factor of the value of a digit. The words, for example, thousands, hundreds, and ones are indicating the place values of the digit. So let us see if we have that right down, because that might be just a mouthful. We have 2,479. In this case, the number or the digit furthest to the left is going to have the largest place value. And the place value is the greatest determining factor in the value or the overall value of the digit. The digit 2, being the farthest to the left, has the greatest place value, and hence it has the greatest value overall. The answer is therefore option A. The second thing that the value of a digit is dependent on is its face value. The face value is dependent on the digit themselves. The digits in the number, therefore, have face values of, there we have them, 2, 4, 7, and 9. If two digits have the same place value, the one with the greater face value is greater. So, say for argument's sake, we have another number here, and we have same number of digits, and we have a 5 below the 4 right here. They have the same place value. But because 5 is greater than 4, we know that the 5 has the greater face value. Therefore, the 5 will have the greater value overall. However, what do we have on our statement here? If two digits have the same place value, the one with the greatest face value is greater. However, no matter the face value, the digit with the greater place value is always greater. What is 5200209 in words? I don't want to spell it out as yet because I don't want to call the number correctly and then we are wondering how I arrived at it. We'll see how we solve this problem first before we are going to call the number out in the correct way. So let us go. We have our number there, and I'm not going to call it out either. Let us first indicate the place values of the digits. And there we have them. We will begin at the digit with the largest place value. It is 5 and it is in the millions place, as we can see right there. So it's in the millions place, so it's 5 million. Second digit is the 2 and it is in the hundreds of thousands place. Right. So 200,000 because it's in the hundred of thousand place or the 100,000s place. The next two digits are zeros. So we go straight to the 2. Alright. Now that we have said that this one is what? 200,000. This don't mean that we have a 10,000 right here. Why? Because the 10,000 position is occupied by a 0 and the thousands position is also occupied by a 0. So we move right down to this 2, which is 200s. So we have 200s right there. 200. And of course the next digit is a 0. So we go straight to the 9. The final digit is always in the ones place. It represents 9 ones. So we just say 9. So 209. So the entire thing is 5,200,209. The answer is option C. So which set has only proper fraction? As a matter of fact, what is a proper fraction? A proper fraction is one in which the numerator, which is the top number, is smaller than the denominator, which is the bottom number. If the numerator is larger, the fraction is improper. So we have to find among the options the set in which all the numerators are smaller than denominators. Of course, you may just be able to just look at this and tell. So you can just look and say, well, that looks like option D. But let's look at that. Option B contains 2 improper fractions. It is also incorrect. So our first one that we have right here has a single improper fraction. So we know that is not our answer. And in option B, we have all of 3 improper fractions. So we know that one is out. And by the time we get to option C, all of the fractions are improper. So we know that's not right. So all of the fractions in D are proper. This is the correct option. This one is saying which is $22,107. Jerry, look at this one. with the dollar sign at the back. Of course, when we are talking, we call the numbers and then we put the dollars at the end. So we are going to say what? $22,117. We don't say dollars 22,117. But I don't know of anywhere in the world that the dollar sign is placed at the end of the number. So we know that options A and D are incorrect. So we know now that the correct answer must be either option B or option C. When representing currency in dollars, the dollar sign goes first. Good. And of course, we're going to put our place values right inside here. We have 22,000. That means our largest place holding digit must be in the tens of thousands. So that is why we have the largest right here, because we're talking about 22,000. So we know that tens of thousands going to be our largest place value. So we have 22,000. What about 22,000? 22,000 consists of 2 tens of thousands and 2 thousands. So 2 right there and another 2 there. Then what? 100. As we can see there. So in our hundreds column, we are going to put 1, 100, and $7. Oh, so, and 7, good. Therefore, the 7 is what? 7 ones. There is no tens. But we have to account for the fact that there is no tens, because all of the digits and their placeholders have to be represented. So, $7 represents 7 ones. And of course, what do? The tens position has no number, indicating that there is no tens. A place holding 0 is used. The tens position has no number, indicating that there is no tens. A place holding 0 is used. And we are saying that a second time for emphasis. The correct option is C. How many even numbers are between 19 and 25? An even number is a number that is divisible by 2. These numbers end with the digit 0, 2, 4, 6, or 8. So of course, what do we do first? We are going to put down the numbers 19 and 25. And then we are going to put the numbers between them. Those are the numbers that are between 19 and 25. And how do we identify the even numbers? An even number will end with a 0, a 2, a 4, a 6, or an 8. Those are the even numbers. So this one is ending with a 0, so it's even. This one is even, and that one is even. How many of them? Jerry, look again. Pay special attention, else we'll count them and you will not see what happens. Okay, so we have 3 of them. The correct answer is therefore option C. What is the reciprocal of 2 and 2/3? And we have a lot of answer here. 8/3, 3/8, 2 and 3/2, and all of these. But what do we do? To find the reciprocal of a fraction, interchange the denominator and the numerator. That's how we find the reciprocal of a fraction. The figure that is given is a mixed number, so we need to express it as an improper fraction. Right? So we have not concluded on our numerator and denominator as yet, because we have a mixed number. So we have there a whole number part, because it's a mixed number. And of course we have a numerator. And of course, our denominator. What do? Multiply the denominator by the whole number, then add the result to the numerator. That's how we are going to do it. So we're going to say now 3 times 2 is equal to 6. And then we say 6 plus 2 is equal to 8. So the numerator is going to be 8 and the denominator will be the same thing. So the denominator is the same as the one that we have right there, which is 3. So now we are going to do our reciprocal. We may now reciprocate the fraction. To reciprocate a fraction is to find its reciprocal. And Jerry, don't try to do this on the board or in your book. It will not work. I know what you'll do, Jerry. You'll cut the numbers out. So you cut them out on a piece of paper. As I say, reciprocate, you will just spin them around like that and get the answer. And you can do it just like we have it on the computer. The answer represents 3/8, and this is option B. Of course, we can find the reciprocal of whole numbers also. So let us find the reciprocal of the whole number 6. 6 may be written as a fraction whose denominator is 1. So of course now we may do that. So let us find the reciprocal of the fraction by causing the denominator and the numerator to exchange places. So the new fraction is 1/6. So whole numbers may also be reciprocated. Here is a big term. Another term for the reciprocal of a number is its multiplicative inverse. Say that, multiplicative inverse. New term for you, Jerry. Which is in descending order. What does it mean to descend? To go down, to get smaller, right? When the sun is descending, the sun is going down. And of course, if we are going in descending order in a scale, we are going down. So, which one begins at the largest value and ends at the smallest value? Well, with this technology that we have right here, we can devise 100 ways of getting it done. So this is just one of them. It is not impossible to look at the problem and write the fractions in descending order. Although even for Jerry Lewis it would be too much of a challenge to do that. However, writing the fraction with a common denominator makes it easier. So, all the fractions in the 4 options are the same. So because the fractions are the same, we know that whatever values we are arriving at in our solution, these values will be the same for the set of fractions that we are using. So find the LCM of the denominators, that is the smallest number that all of them can divide into without leaving a remainder. So the common denominator, or the LCM, is 20. And of course we are going to do more or less the same thing that we generally do when we are adding fractions. So the first one that we are going to say is 4 into 20, and that gives 4 into 20, 5. And then we say what? 5 times 3, 15. So see, 4 into 20 is 5. Full stop right there. 5 multiplied by 3 is equal to 15. 15 goes there. That is basically how we generally arrive at the number when we are adding fractions or subtracting fractions. So 10 into 20 is 2, and then 2 multiplied by 3 is 6. Like 10 into 20 is 2, and then 2 times 3, 6. And 5 into 20, that's 4, and 4 times 2 is 8. And finally, 2 into 20 is 10, and 1 multiplied by 10 is 10. Or we may say that half of 20 is 10. So here we have the fractions, and of course we have placed these fractions with a common denominator, and these are the resulting numerators. Of course, to descend means to go down. This means that we will start with the largest fraction and end with the smallest one. The largest fraction is associated with the largest number of the common denominator, the largest numerator of the common denominator. So of course, we have this is the largest number, and it's associated with 3/4, so 3/4 should be the largest one. And of course, among the others, we are going to look for the largest one, and that's 10, and it's associated with a half, so a half is next. Then of course, between 6 and 8, 8 is larger, so 8 is associated with 2/5, so we are going to write 2/5 there, and of course the other one will just go automatically down right there. We have confirmed that the correct answer is in fact option D. So option D has the fractions as we have them right here. And of course, the order was determined by the size of the numerators when we have chosen an appropriate common denominator, which of course is the LCM of the denominators that we had to begin with. So option D is correct. Which will complete the sequence? Examining the polygons, because what we have right there, a sequence that consists of what? Polygons with numbers inside of them. So let us examine the polygons. It can be seen that the first is a triangle, 3 sides, the second is a square, 4 sides, and the third a pentagon, 5 sides. The next shape should therefore follow the sequence 3, 4, 5. It should therefore have 6 sides. A 6-sided figure is called a hexagon. Options A and C are hexagons, and one of them is right. But which one? Let us take a look at the number sequence. The number sequence is 1, 2, 4. The numbers in the hexagons are 6 and 8. So let us choose 6 and see if it is consistent with the number sequence. Now, let us use an addition. Say we are going to be adding, say 1. We have 1 plus 1 equal 2. Then we have 2 plus 2 is equal to 4. So we are going to be adding 1. Then we add 2. Then we add 3. The next number to be added should be a 3. So 4 plus 3 is equal to 7. This is not in any of the choices. So we know that we cannot arrive at the answer by just adding and increasing the number that we are adding by each time. So we know we have to throw that one out. We may therefore opt to use multiplication. 1 multiplied by 2 is equal to 2. Then of course 2 multiplied by 2 is equal to 4. If each term in the sequence is to be multiplied by 2, then we need to multiply 4 by 2 as the final one. So 4 multiplied by 2 is equal to 8. Right there. Therefore, the shape is a hexagon and the number involved is 8. This is represented by option D. Which term best describes the set of numbers? We have that set of numbers 2, 3, 5, 7. So let us consider option A. The numbers are not all odd. So the best, that is what option A is saying, that the best term that describes those numbers, the set of numbers, is odd. But of course, we have a 2 there, and the 2 is an even number, so the numbers are not all odd. So odd numbers are those numbers that are not divisible by 2. We can identify them by the fact that they end with the digit 1, 3, 5, 7, or 9. Option A is not the answer. Option B is not the correct answer. The numbers are not all even. Even numbers are divisible by 2. We can identify them by making use of the fact that they end with 0, 2, 4, 6, or 8. A prime number is one that has only 2 factors, itself and 1. This means that it is only divisible by itself and 1. Or we may say that only itself and 1 can divide into it without leaving a remainder. All of the numbers in option C satisfy this condition. Option C is therefore correct. Don't forget that 2 is the only even prime number. So option C is correct. What about D? Mixed numbers are those numbers that have a whole number part and a fractional part. Examples of mixed numbers are 5½ and 2 3/4. No mixed number is present in the set. So we do not have any mixed number in this set. So we are sure that D is not correct. Which ratio is equivalent to 51 to 34? This problem will no doubt require that we reduce the ratio, because as a matter of fact, the ratio that we have here is not represented over here, not in its original form. The greatest problem that we face is to find a common factor. This might appear ridiculous, especially that 51 appears to be a prime number. 51 is not a prime number. It is a multiple of 17. 34 is also a multiple of 17. So we may therefore reduce the ratio by a common factor of 17. 51 divided by 17 is 3. And of course, 34 divided by 17 is 2. The correct option is 3 to 2, which is represented by option A. What is 452 written in exponential form? 10 squared, or 10 to the power of 2, is equal to 10 multiplied by 10. And of course, 10 multiplied by 10 is equal to 100. The exponential form of 100 is therefore 10 squared, or 10 to the power of 2. 10 to the power of 1 is equal to 10. The exponential form of 10 is therefore 10 to the power of 1. Any number raised to the power of 0 is equal to 1. And this applies to 10 also. The exponential form of 1 is therefore 10 to the power of 0. It might appear to be some scrambled bit of information, but of course we're going to make it plain by writing them down in a visually friendly form. So write down the number 452. Write down the place values. Replace the regular place values with their exponential form And we know them that hundreds, the exponential form for 100 is 10 to the power of 2, but we are going to begin with the lowest one first. So the exponential form of 1 is 10 to the power of 0. And tens, 10 to the power of 1. Hundreds, 10 to the power of 2. The answer may now be written in exponential form. Here we have it, 10 to the power of 2 here, and we have it for accompanying the 4 very nicely there in blue. So 4 times 10 to the power of 2, and in red we have 10 to the power of 1 accompanying 5. So we are going to add 5 times 10 to the power of 1. And what will happen? In green, we have 10 to the power of 0 accompanying the 2. 2 times 10 to the power of 0. How is it represented here? Which one is correct? The answer is option B. What are the prime factors of 18? Nine is not a prime number. Therefore, all the options that contain 9 are incorrect. How do we know that 9 is not a prime number? Well, of course, if we eliminate the 9s, only option C will be left. So, the correct answer is therefore option C. Good. 9 is not a prime number because a prime number has only 2 factors, itself and 1. However, 9 has more than 2 factors. Apart from 9 and 1, 3 can also divide into 9 without leaving a remainder. What about 2 and 3? They are both prime numbers because each of them has 1 and itself as the only factors. Also, both of them can go into 18 without leaving a remainder. So, although we have proven by contradiction that C is the correct option, a direct examination of the option shows that it is correct also. Just a note to remind you about factors. A factor is a number that can divide into the other without leaving a remainder. Factors of 20 are therefore 1, 2, 4, 5, and 10. Of course, 20 is also a factor of 20, because if we divide any of those numbers into 20, we will not get a remainder. Factors of 12 are 2, let us begin with 1. Of course, 1 may go into 12 without leaving a remainder. Let us begin with 1. Of course, 1 may go into 12 without leaving a remainder. So we have 1, 2, 3, 4, 6, and 12. 12 is divisible by all of those numbers. This means that each of them can go into 12 without leaving a remainder. So that's just a little note on factors, so that next time we might be able to identify factors of other numbers. If 20 chairs are shared equally among 5 girls, which would give the number each girl received? We have solved many similar problems in different forms. The information may be written in the form of the following mathematical statement. 5 girls, 20 chairs. To show how many chairs one girl will get, we need to divide 5 girls by 5, because 5 by 5 will give 1. This adjustment is maintained throughout the statement, and the other side is also divided by 5. So we are going to divide both sides by 5 because we need the number of chairs that one girl will get. So on this side, 5 girls get 200 chairs. So to get 1 girl, we divide 5 by 5 and we are going to get 1. So we do the same thing on the other side. Finally, we get 1 girl 200 chairs divided by 5. This is the same as 200 divided by 5 expressed in option B. The answer is represented by option B. Some teachers want their students to be aware of the use of certain words in a question. The word each is usually included when division is required. This one is one of my favorite, but I can tell by looking at Jerry's face that he does not have any favorite problem at all. All problems are very harmful to him, so he will not choose a favorite problem to solve. Poor Jerry. Which Venn diagram best represents the relationship between the sets? So let us represent the sets pictorially. Lovely. Set P, 1, 3, 2, 4, and set Q, 3, 4, 5, 6. The elements 3 and 4 are present in both sets. These elements can be shown to be shared by the sets if the sets are brought together. So if we are going to take the sets together, put them together, unite them somewhat, 3 and 4 will be the elements that are going to be shared by the two sets, and that will be demonstrated. While I was working on this particular problem on the computer, Jerry insisted that I could never get those digits to come together, and that is why this one is my favorite, because I defeated Jerry Lewis in getting the digits to come together, and he claimed that it was totally impossible for me to do that. So let us put them together. See, they are brought together again. Option C is correct, as it shows the two sets sharing the common elements. Yes, when representing sets and there are elements that are common, the most appropriate way to express that is to cause the common elements to be shared by the two sets. And if we have a 3-set problems, the common elements should be shared among the 3 sets. And of course, having the sets joined together in such a way in which one overlaps the other might be one way to demonstrate it. As a matter of fact, it is the best way to demonstrate that. Option C is correct. Which represents the union between the two sets P and Q. So let us represent the set as before. Of course, if we are doing the union, because in the union of two sets, no element can be repeated, the most appropriate way is still to bring the two sets together. So even for this new question, the previous representation of the two sets is also the best. Put them together again, and we are going to write down all the elements that are involved in the two sets taken together. That is going to be the union. So the union of the two sets is the set that contains all of the elements of both sets taken together. This is done without repetition. The diagram shows the elements of the union clearly and without repetition. The union contains 1, 2, 3, 4, 5, 6. The correct option is A. So I defeated you again, Jerry, by bringing the sets together on the computer. Any more challenges?